developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
One of the big challenges in space is communication. We're increasingly using space and we're going further out. And so there's a big need to have large antennas that can capture weak signals. And to do that, you need structures larger than what you can fit inside a rocket and deploy. Therefore, you need to do in-space manufacturing. And when you do in-space manufacturing, you need to have the materials and the processes to make lightweight structures that then can be assembled, typically by robot, into a large structure. So strategically, we're trying to enable higher space situational awareness for the Space Force. But more tactically, what we're trying to do is we're trying to expand the chemistry of those materials that can be used in it. So we are going to start looking at blends of dicyclopentadiene and epoxy, which have recently been shown to have some synergistic properties. And we're doing things right now with dicyclopentadiene, and we're going to epoxy, which is better in adhesion for fiber and more space durable. And we hope to put a new option on the table for space in-space manufacturing.
The size of future antennas are anticipated to reach 100 meters or even larger than that. So rather than folding, transporting, and deploying them into space, future missions require these to be manufactured in space. Manufacturing of composite elements in space with robots that assemble them into superstructures requires novel materials and processes. Researchers at the University of Illinois and Jeff Baur's team are currently developing such capabilities for the DoD. Combined with the understanding from epoxy resins at AFRL, we will create new formulations capable of low energy processing with improved space durability, fiber resin adhesion, and lower outgassing. Thanks to the funding from the AFRL Regional Network, we have been able to form a great and potentially impactful partnership to meet AFRL needs.
The main properties we're looking for in our resin is a low energy and a fast and efficient cure. This will be done by using frontal polymerization.
DCPD has low viscosity, easy composite processing, low energy curing, good toughness, but poor interfacial carbon fiber properties.
Epoxy, on the other hand, is a much more viscous and stickier resin that adheres well to carbon fibers, and it has been studied very well at both the Air Force and just in space in general.
We have hypothesized that DCPD and epoxy co-cured mixtures will have a good balance of processability, such as low viscosity, low energy curing, and improved composite mechanical properties in comparison to either DCPD or epoxy alone.
We want to first find the formulation with the best balance of properties. We define best in terms of viscosity and volatility of the liquid formulation and compatibility and thermal stability of the cured resin. In short, we have found a range of DCPD epoxy compositions that achieve these goals. Soon, we will investigate the thermomechanical behavior of the carbon fiber composites of these blends.
The viscosity of our mixed resin needs to be low enough to be readily infused into carbon fibers, and we found that all of our formulations appear to have a low enough viscosity to be easily infused. We then looked at the volatility of our uncured mixtures as measured by weight loss as a function of temperature. We found that liquid formulations having 12 to 20 parts by weight of epoxy resin per 100 parts of DCPD or 12 to 20 parts per 100 show relatively low volatility in the range of temperatures we would cure the liquid resin under pressure. In formulations above around 20 parts per 100 epoxy, we saw a sharp increase in weight loss beginning around 100 degrees Celsius, which is below the maximum processing temperature of 150 degrees Celsius. From these observations, we chose to focus on that range of 12 to 20 parts per 100 formulations for the subsequent cure kinetic studies. We used differential scanning calorimetry, or DSC, to investigate the curing kinetics of the down-selected resins. DSC revealed two curing peaks. The first peak, centered around 71 degrees Celsius, is associated with the curing of DCPD, and the second peak, that was centered around 108 degrees Celsius, is associated with the curing of the epoxy. When we heat the mixture to 150 degrees Celsius and hold, both materials cure into network structures that may or may not have separated phases. We prefer to see a single phase in which properties will be homogeneous. We first looked at phase separation or resin compatibility as measured by cloudiness after cure, since the two polymers are both clear when they're cured alone. We observed that the samples within that 12 to 20 parts per 100 epoxy range are clear after curing and thus compatible at the macro scale. We next looked at thermal stability of the cured resin as measured by weight loss as a function of temperature, in which the 12 through 20 parts per 100 epoxy formulation range are shown to be thermally stable up until around 300 degrees Celsius, which is much lower than the temperatures expected during process of service in space, and suggests the two polymers are highly cross-linked. We are currently evaluating the thermal mechanical properties of these thermally cured resin using DSC and dynamic mechanical analysis, also known as DMA.
In the future, we will compare the properties of thermally cured resins with those that are frontally cured using either UV-initiated, radical-induced cationic frontal polymerization of epoxy, similar to what AFRL is doing, or by frontal ring opening metastasis polymerization of DCPD. We would like to understand how the properties and the relative energies needed change as a function of the initiation method. We will also begin to infuse these carbon fiber preforms using vacuum-assisted resin transfer molding, also known as VARDM, to create prepregs that can be cured into composites in a manner that simulates space-based manufacturing. So in conclusion, we have a range of DCPD epoxy formulations which look very promising for in-space manufacturing composites and expands the range of useful chemistries that will help the Air Force build large and efficient structures in space.